Ladies and gentlemen, our class recording for today has begun. Let me do this, then I'll do this, and I'll do this. Okay, on Monday, we introduced the idea of an orbital diagram. And like it says up on the title sheet from the slide presentation that we did on Monday, where do these electrons go? On Monday, we talked about three rules, or three sort of principles that we use that determines, or we use them, they go into determining where these electrons ultimately end up and what our orbital diagrams look like. So tell me about one of those rules. Roger, do you want to take one?
Sure.
Right, so, first one.
The off-bow principle.
Off-bow principle. Off-bow principle states
Orbitals are filled from lowest energy
orbitals filled from lowest energy
to highest energy.
to highest energy, meaning which orbitals get filled up first? One's closest to the nucleus, because those are the lowest energy. Okay, so off-bow principle. All right, what's another one that we talked about on Monday? Go ahead. The Pauli exclusion principle. What does Pauli exclusion principle tell us, Amanda? Each orbital can only contain 2 electrons. How do we distinguish one from the other in an orbital diagram? One up arrow, one down arrow, right? Third rule. Hund's rule. What does Hund's rule tell us, Kenny?
You'd have to have one electron in every household before you can put down the
You got to have one electron in each orbital in the same sublevel before we start pairing up. So electrons will distribute themselves as evenly as possible as long as they can. Good there. Okay. On Friday, are we here? Yep. Okay. Monday. On Monday, we started filling in some of these orbital diagrams. On page 3, which starts with sodium up at the top, okay, we skipped a couple. One of the ones that we skipped was phosphorus, letter H, which is on page 3 of your outline from Monday. I would like you to work with the person next to you, use your periodic table and the orbital filling chart that's on the front of your outline to write for me the orbital diagram for phosphorus. Go! Phosphorus up on the board. Okay. Brooke, question. Go ahead. you have to show me somehow that all three of these are 2p orbitals, okay? So you could label each one separately as 2p, or to save yourself some time, you could do that, but you need to make sure that they're all labeled as 3p or 2p or whatever it is, okay? Kenny, go ahead.
Are you gonna have any that are gonna go up to like 3 meters?
Well, hold on to that question for a second, and I think I'll answer it for you, okay? So, short answer, no, and there's a reason why, okay? All right, good with this orbital diagram, okay? Before we go on to the next part, I want to do a couple of things to help us review and to make some connections, okay? All right. Remember, this mess all started, right, way back here, yes? Okay? All of these orbitals, different places around the nucleus where electrons could exist, but now we're getting into where exactly are electrons, okay? This orbital diagram is a shorthand way of representing this picture, right? Or maybe more something like this picture where we have electrons in specific orbitals. Yes? Okay. Here's what I want you to do. Nope, this one. All right. I have highlighted one electron in this orbital diagram for phosphorus. I would like you to, with the person next to you, knowing what we talked about last week and reviewing some of the stuff that we did, what are the quantum numbers that go along with that electron? Discuss with the person next to you. Go. I'll write it up here, don't worry.
What's L?
Oh, L's.
You're confused about what? You get that far?
And M goes from negative.
And then those weird ones that are but we don't have them.
M, I don't know how to say M. N is the second.
That's exactly what I thought.
Okay.
L.
All right, let's discuss. All right, let's discuss, please. So, first, the stuff I have written on the board. Is that the right answer?
It's an acceptable answer.
It's an acceptable answer. There are lots of acceptable answers for this one. Okay? So, first, there are two that always have to be that have to be the same on everybody's paper. What are the two that have to be the same? N has to be 2 because it's in the second energy level, and L has to be 1 because it's a pedal orbital, it's a p orbital. Okay? So go ahead. Yep, because it's 2p. Yep. All right. The next, and if you're good with those two, that's a good start. Okay? And most likely we'll get you through the test tomorrow. Okay? But let's talk about the last two. M the m value tells us which of the p orbitals is that electron in. And we said that it's got a different m value, whether it's the x, the y, or the z one. Do you know which one's x, y, and z from this picture? Not really, okay? So, in this case, we really could be talking about any one of the three. So it could be 0, or it could be positive 1, okay? Any one of those values would have worked for m, okay? S, does it matter what S is? No. Okay? Because it only becomes important when we're talking about what? When we're talking about two electrons that are
In the same order.
in one orbital, in the same orbital, okay? All right, ready for the next one,
Maybe.
okay? All right, write me quantum numbers for those two, the one that I highlighted in blue and the one that I highlighted in yellow. Go.
L is 1, M can be like -1. It's the same thing. Alright? No?
I think
M would be different.
I would know it's the same.
M would be positive 1 and S would be -1/2.
You guys are ready, huh?
On the yellow one, would it be on the M would be positive 1, and then S is -1/2. Yeah, we got that right.
Okay.
We got that.
All right. I'm giving it a couple more. Let's give a couple seconds. All right. If you got that, that's good. Okay. If you got that, that's good.
Is it okay if I put positive on this?
It's different from the ones that are other than. Yeah, they're not the same. One that doesn't matter. Everything has to be different.
Those acceptable answers.
All right. So. All right. Good. Continue talking. So. First, acceptable set of answers written up on the board. Not the only acceptable set of answers, but one acceptable set of answers. Okay. The one thing that we really could change in this blue and yellow would be what? M would be the one that we could change, right? We could also change S, but what has to be true about the S value for those two? They have to be opposite, because we're talking about two electrons in the same orbital. Okay? Julie, go ahead.
Okay, so do the blue and the yellow, the values of M have to be different than, they can't be the values of pink.
Correct. They have to be different than pink, but
They can have the same S value.
not, they can have the same S. Yes, because remember, S only applies to two electrons that are in the same orbital.
Okay.
So going back to the M value, though, finishing that statement, the M value for blue and green, or blue and yellow, have to be different than purple, but finish the sentence, but the same as each other, because blue and yellow are both in the same orbital. Yes? Because they are in the same 2p orbital. Okay. the M value for blue and yellow must be different than purple, but must be the same as each other. Say again? Pink, purple, whatever. Yeah, that's more pink. Yeah. Sorry. That's more pink. So yeah, okay. All right, Alex, go ahead. Yep.
When you get out of the petals, like it's not sticky, then you get into the leaves,
Yep.
then can it extend to more than -1, 0, and 1?
Yes, because
-2, -1, 0, 1.
yes, because there are
One of those -3, 1, 0.
yes. That is beyond the test though. Okay, definitely beyond the test. All right. I want to show you guys something. Okay? No. I want to show you guys something and make some connections hopefully, okay? All right. So, this picture right here, this picture that we have up on the board right now, right?
What'd you do? You did the thing.
Okay.
You did the thing. Wait, that's a weird part we've been waiting for.
Well, I mean, you know. So. All right.
It got weird.
But using this as a transition to the last part, okay? This is a pretty detailed picture of orbitals and electrons within those orbitals. Okay? It shows shapes, it shows how they're oriented in relation to one another, it shows relative sizes, right? This is a pretty detailed picture of orbitals and electrons within those orbitals. This is also a picture of orbitals and electrons within those orbitals. Not quite as detailed, but knowing what you know about the previous picture, you can make some assumptions. You make a picture in your head. Okay? But on Monday, the last thing that we did in class was to draw the orbital diagram for manganese. Okay? Down at the bottom of the page, right? And it was really long. And it was only 25 electrons. There are atoms on the periodic table that have up to 92, 103 electrons. Orbital diagrams for those atoms could get pretty out of control. So, the last thing that we do to continue to shorthand representation of this picture, we call the electron configuration. All right, so this is the last page of your outline that I gave you on Monday. For some reason,
So we're not doing sodium or going on
no, we'll not in class. We'll do that a little bit later. All right, first, I'm not sure why you got that last page on your outline. It's just a blank page. You can tear it off if you want to. You can keep it on if you want to. You can make a paper airplane out of it as long as you don't throw it at anybody, hit it in the eye, whatever. Okay? All right. So, let's get this done here. All right.
This is going to be on class.
Yep. So you'll see though that based on what you know up until this point, yeah.
Okay.
We should, yeah. Both of the other classes flew through this today because it really is, like I said, it's representing the same thing that we've done over the past week and a half, just in a shorthand version. Okay. All right.
So it's like
So.
shorter than this.
Yep. Easier than that. All right. So electron configurations, a shorthand way of representing the location of electrons around the nucleus. It's another way of representing that multicolored picture that we drew back last week, okay? But it's not as detailed, even as the orbital diagram, but it is a good way of showing patterns, especially if you already know the theory behind where it all comes from, okay? So, with that being said, let's go here. Got here, let's go here. Okay. First orbital diagram that we drew was hydrogen. And it was pretty simple, right? Because how many electrons does hydrogen have? One. Okay, so we have to represent that one electron and its location in the electron configuration just like we did in the orbital diagram, but in a little bit shorter fashion. So, we learned over the course of the past day and a half right? That what's the first orbital that gets filled in any atom? 1s. So we start off and we write the name of the orbital, 1s. No line above it like an orbital diagram. We just write the name. And then we represent the number of electrons that is in that orbital with a superscript. So, how many electrons are in the 1s orbital for hydrogen? 1. So we write a little 1 up here like this. Okay? 1s1. Okay? The next one we did was helium. How many electrons does helium have? 2. We know from our orbital diagram, both of those electrons are in which orbital? So we start off, we write the name of the orbital, 1s, but how many electrons does it have in it? 2. So we write a 2 up there. Now, when we pronounce that, we pronounce it as 1s2. It's not 1s squared. Okay? It's not a mathematical operation. It's representing a number of electrons. Even though it doesn't specifically say it in this electron configuration, what do you know about those 2 electrons? Opposite spin, right? S plus 1/2, S minus 1/2, right? Pauli exclusion principle. Still applies even though it doesn't specifically show it here. Okay? It's a shorthand way. It's not as detailed, but it still gives us the same information. Okay? Next orbital diagram that we did was lithium. We know that lithium has how many electrons? 3. The first 2 electrons in any atom go in which orbital? 1s2. Where does the third electron go? 2s. Why does it go in the 2s orbital? There's no more room in the 1s orbital, and why does it go to 2s next? It's the next lowest energy. That's called what? Audrey, you told us in the beginning of class? Off-bound principle, right? How many electrons are in the 2s orbital? Okay? Good there. All right. Now, let's make it a little bit more difficult. Okay. So we'll skip boron and we'll go to carbon. Okay? We learned the other day carbon has 6 electrons. Amanda, the first 2 always go where? Okay, so 1s2. The next 2 go in 2s2, because 2s can only hold 2 electrons. Then we go to 2p. Now, here's where electron configuration is shorthand. We talked about it in an orbital diagram. How many 2p orbitals are there? 3. And we write all of them. But in the electron configuration, we don't write all of them. We just write 2p. And then, how many electrons are in the 2p sublevel? There are only 2. Knowing what you know, though, right? Knowing what you know, what has to be true about those 2 electrons? They're in separate orbitals, petals, okay? They're in separate orbitals. That's what? That's Hund's rule. Even though we don't show it here, Hund's rule still applies. Okay? Good so far?
Can we just write it out like you want to?
You can't, well, no, because you need to know both of them. All right? Just give us a couple more. We'll go, okay? All right. Valentina, go ahead. Because how many electrons total does carbon have to have? 6. Okay? Periodic table, yes. 2 here. 2 here. and that means 2 here. Okay? If we add up all of these superscripts, we should get the total number of electrons that are in that atom. Okay? Oh, so go ahead.
So if you try like 3, would it just for the pedal, it would just be 3?
Okay? Yeah, hold on to that, and we'll show you. I'll show you that in just a second. But yes, Julie, go ahead.
So, basically what Alex was saying,
Yep.
basically the original 6, it can be any of that, the X1 or superscript can go up to 6.
Yep. So, let's do neon. Look at your periodic table. Find out. Okay. All right. So neon has how many electrons? 10. Okay. The first 2 electrons always go where? The second 2 electrons go. Then we have how many left? 6, right? Okay?
I get it.
All right. What? Okay.
I made connections.
Good. Write me the electron configuration for sodium. Go. All right. First, are we okay with this electron configuration for sodium? It's number 11. Way over on the far left.
It's like Na about a
All right. But on your outline, if you look underneath sodium, it says noble gas configuration. Let's go here. Okay? Okay. So, first, let's talk about the top one. Neon. Neon has 10 electrons. It puts us into the second principal energy level. But in the second principal energy level, there's 1 s orbital, 1 sphere, right? 3 petals. It can hold a total of 10 electrons. Does that make sense? Sorry, 8, my bad. 2 in the sphere, 6 in the p's, right? Okay. But once we max out the p orbitals, where do we have to go? Do butterflies exist in the second energy level? You have to go up to the next one. Butterflies don't exist until we get to the third, right? So, the second energy level is completely full. Okay? So, what we can start doing, even though this is much shorter than writing an orbital diagram, we can make it even shorter. And the way that we make it shorter is by starting off and writing the formula for the noble gas, which is the last column on the periodic table. We put it in square brackets, and that represents the first 10 electrons, because that's how many neon has. And so then we pick it up from there. So the only thing we would have to write then after that would be 3s1. Now, hold on one second. Okay, go ahead, Angel. So, do you understand that the first 10 electrons for neon and for sodium are exactly the same? Okay, so what we can do is, Now, neon is part of the last column on the periodic table, okay, which is called the noble gases, right? And what we see there is that, Angela, and we'll see this pattern more and more as we get into more higher units, we deal with bonding and stuff like that. Their s orbitals and their p orbitals are all full. Okay, that kicks us up to another level then, okay? So what we do is we can shorthand that our electron configuration for sodium, because neon represents a full set of 1 and 2 energy level. And then we can just pick it up from there. Okay? Now, hold on, let me do this part, and then I think, okay. So, now, this isn't on your sheet, okay? But the next element that shows up on the periodic table is magnesium. And magnesium has 12 electrons, okay? You can't do this. Okay? You can't do that because this doesn't represent a full set of S's and P's. It's not a noble gas. But you can do this. Okay? You can do that. Does that make sense? Okay? Noble gases are the ones in the far right. Alex, go ahead. Yep. You could helium. You could, and technically that would be fine, but this is a way of making it shorter. Right? Writing 1s2 or putting helium in brackets, it would be fine. Yeah, that would be okay. Yeah, well, I mean, it's just a matter of is it shorter or not. And writing 1s2 versus writing helium in brackets, basically the same thing. But if you get up to, when you start getting up here, now it makes a significant difference in how much you have to write. Going back to your question from before about the 3 electrons in the p level, right? Okay, here's phosphorus, right? Here is our orbital diagram for phosphorus that we drew right at the beginning of the period today. Write me the electron configuration for phosphorus. Either the full electron configuration or noble gas configuration. I don't care. What would the electron configuration for phosphorus look like? Easy, easy, easy. I told you you could write either one. You could write a full electron configuration or a noble gas configuration.
Could you do hydrogen and then
Helium? Hydrogen only has 1 electron. It's not a full.
I mean not hydrogen.
You could do helium. That's
Magnesium.
no.
Because it's not a perfect. It's not
Right.
I did that. Yeah, and then
Okay. So go ahead.
Okay, so basically until we get to data, we're gonna use either neon, so that's the only noble gas that has units on them.
Right. Okay. Yes.
I get it now.
That's where we're going next.
Okay, I understand now
All right.
because
So either one of these. Couple more minutes. Either one of these would be fine for phosphorus. Okay. Alex, going back to your question from before, right? 3p3 at the end. Okay. Even though we don't show it in the electron configuration, how do those 3 electrons have to be distributed? One in each orbital, right? Even though, because that's Hund's rule, right? Okay, so yeah, even though it doesn't show it, that's how we write it, okay? This is the electron configuration. It doesn't show as much detail as the orbital diagram, But knowing what we know about Hund's rule and things like that, we should get there. Okay? All right. Go ahead.
The element that has 3p to the 6th, then we could do that in bracket, right? Is this the element that has 3p?
Okay.
Yeah, it is.
Nope. All right. Next one that shows up on your sheet, I believe, is argon. Yes? Okay. So, okay, you can do that. Or
So you can just use any equals 10.
any equals the first 10. Okay?
Oh.
Then can we use the next? Well, when we go to 4s,
Well, no. That's cheating. That's cheating. It is a noble gas, yes. So what Jillian is saying, if I asked you to write me the electron configuration for this, could she just do this? Well, I'll tell you, I'm not going to put that on the test. How's that? So,
But do like size of so that's not incorrect.
technically, no. All right.
wait, so is calcium be like the next?
Okay,
20?
well, let's go then.
4s.
The next one that we did we actually drew the orbital diagram for potassium. Okay, so now, Kenny, argon's going to represent the first how many electrons? 18, right? So we could start with argon, okay? But, right?
Can you start with neon still?
You could if you wanted to, that's fine, okay? But if we can go up a whole level, then that makes our lives even easier, okay? Now, last thing we talked about this on Monday, right? These are 3p. Argon has 3p already full. But if you go up the chart, even though there are 3d orbitals, is that the next one that you hit on the chart? No. So this would then be 4s1. Okay?
Like,
The last one. Yep. Okay? So, easy. Hey, you still have 5 minutes left. Alright, the last one that we did the other day in class was manganese. Okay? And we drew the orbital diagram for it.
wait, so things with 3p can go up to 10?
Yep. And there's our electron configuration for manganese.
That matter.
Wait, how
So-
many 3ds are there when you line it all out?
Look at the front of your, look on the front, no, front. Next to 3D, how many lines are there?
Oh, okay, that makes sense now.
Libby, go ahead.
What about the alpha principle and the
Okay, the reason why potassium, the reason why it says alpha principle by potassium, right, is because even though we've gone 3s and then 3p being full with argon, right, the next level that we come across isn't 3d, it's 4s. Off-bow principle is just following the chart in order from bottom to top, right? So that's the idea, right? That even though it may be in the 4th energy level, it still has less energy than the d orbitals of the 3rd energy level. Okay? Can you go ahead?
No, like you could have 3D 25.
No. You could have 3d
Oh,
10. Okay? No. All right, so last thing I want to say before you guys take off for today. Okay? So here's pep talk. Okay? Pep talk. We started this a week and a half ago. Okay? And hey, let me give you your pep talk, all right?
heads up.
right? It started like this, right? It was simple enough way back then, right? Over last week, right? We got it all the way up to here. And there was a lot of questions, there was a lot of confusion, but we fought through it, right? And then we added this, right? We started adding the numbers on, and at the beginning, right? Okay? But then today, right? You guys whipped out the orbital diagram for phosphorus like this, right? Electron configurations, we're like, oh yeah, good, yeah, no problem, right? It's come along. Hey, moral of the story, right? This is hard stuff. There are juniors in this building doing it right now in Honors Chem who are struggling with it, all right? You guys have come a long way, all right? So make sure I am very proud of you, actually. This is very hard, all right? So make sure tonight, though, that you study so that when the test comes around tomorrow, you can demonstrate what you've learned, because it's all there, everybody. We just got to get it on the paper, okay?